Alright, silly people, here's the situation. We are in a it's an infinite square well, where the potential is infinite outside of it, and then it is um, zero inside of the well. And so, what we are going to do is we're going to solve the um, Schrodinger equation for the region inside the infinite square well. And that's the Schrodinger equation there. There's no potential inside the square well, and then outside of the well, it's infinity. So there is no wave function outside. So um, Griffiths actually does solve this equation for us. He says that it's a sine kx plus b cosine kx, where k is just root 2me over h bar, and then he uses a couple of boundary conditions to figure out what a and b are. But the boundary conditions for the problem he did are different from the one that we're doing, because he had a well that was just from 0 to a. This is from negative a to a, so it's a wider well. So there's going to be different boundary conditions, different constants, and so we're going to get different wave functions out of it. So um, let's talk about what boundary conditions we have. The wave function has to disappear at each of the boundaries. So we have that psi of minus a should be equal to 0. If we plug minus a into our wave function, we have minus ka plus b cosine minus ka equals 0. And then um, notably, the sine function is anti-symmetric, so that's actually going to flip the sign if you just want to move the negative side out of the argument. But cosine is symmetric, so we can just move the negative sign out of the argument by changing nothing at all. So yeah, there it is, 0. Um, from this, you can get a relationship between cosine of Ka and sine Ka like that, just with a step of algebra. Um, the other boundary condition is, again, the wave function has to be 0 at the boundary, so psi of a also has to be 0. So we have a sine Ka plus b cosine Ka equals 0. And there's two different things you can do here. One of them is you can use this equation, which we derived from the first boundary condition, into this one. And so you can say that 2a sine Ka equals 0. Conversely, you could also plug in this for for sine in this equation. So you can also say that 2b cosine Ka equals 0. Knowing that we have these two equations, we can surmise that there's going to be a situation where a is 0 and a situation where b is 0, and that will change the dependence of k on different integer values of pi. So let's try both options. So the first option is going to be that we set a equal to 0. We're going to call this option 1. And so if you do that, you're going to be left with this equation here, that cosine Ka equals 0. And of course, if you set k to any like half integer, then it will be 0, but there's an elegant way to write that. If you set Ka equal to m minus 1/2 pi, where m is an integer, you'll get 0 for that cosine function, right? Um, and so to write this in a nicer way, what we're going to do is we're going to define a integer called n, which is going to be 2m minus 1. That is, it's an even, no, that's an odd integer. Sorry. It's an odd integer. And from that, we can change this quantization condition around to read Ka equals just n pi over 2. And so we get K equals n pi over 2a. And so if we compare that equation for K that we just got with the definition that we provided based on the energy, and then solve for K, so let's just do that. So n pi over 2a equals root 2m e over h bar, and solve for e is what I meant to say. If you solve for e, you get the same quantization condition for the energy that Griffiths got. That is, it's e equals n squared pi squared h bar squared all over 2ma squared. Okay. So it's nice that it matches what Griffiths got. And we are left with the wave function psi equals b cosine n pi x over a. Right? But we still have to normalize that to find out what b is. So we're going to take the integral of the square modulus of the wave function over all space and set it equal to 1. So we have the integral minus a to a of mod b squared cosine squared n pi x over a dx. That is going to equal 1. We're going to use a trig identity to get through this integral, that just being that cosine squared theta is just 1 plus cosine 2 theta over 2. So that's a pretty quick thing that you can solve. And so just doing that, we've got, now it's mod b squared all over 2, and then a couple integrals. We have an integral of dx plus an integral of cosine n pi, and this should be 2 here and 2 here. Yes, but it's 1 down here, so it's n pi x over a because you multiplied by 2. Right. Cool stuff. Integrate over that dx and then plug in the bounds, set it equal to 1. So these integrals are pretty darn easy because one of them is just x, the other one is a over n pi times sine n pi x over a. And then once we evaluate at the endpoints, we have that mod b squared over 2. We've got a, and then if we plug a into this, we just get sine of n pi, which we know is 0. So then we also have minus negative a, so plus a. And again, if you put a in there, you're going to get 0. So that's it. And then just from a bit of algebra, you can see that b is now just equal to, because this is 2a over 2, it's root a on the bottom, 1 over root a for b. Yeah, we can write the wave function now for that option. Now I'm going to take you all the way back to up here, where we can talk about the second option that we had available to us. which was setting b equal to 0 instead of a equal to 0. That's going to cause some interesting things. Option 2. And let's do it in blue, actually. So if you set b equal to 0, you're still going to have this equation here. So you're going to have sine ka equals 0. You can just set ka equal to any integer value of pi, so we'll say m pi, where m is an integer. And it is useful at this point to first of all solve for k, just say this is m pi over a, but then define a variable n, which is going to be just 2m, that n is an even integer. This is already different from before, so now we have that k equals just n pi over 2a. Again, we get the same k, so we get the same quantization condition for the energy, that is n squared pi squared h bar squared over 2ma squared. So we're still killing it with respect to Griffiths. But now we have the wave function that is a sine n pi x over 2a. And we have to normalize that, and it's the same sort of thing. We have to do the integral over all space of the square modulus of the wave function, set it equal to 1. This time we have mod a squared integral, and it's a integral from minus a to a sine squared n pi x over 2a dx equals 1. And so a different trig identity, but it's going to be functionally the same, that sine squared theta equals 1 minus cosine 2 theta over 2. So plug that into our integral here. We have mod a squared all over 2. We have in brackets the integral dx minus the integral cosine, it's n pi x over a here, dx, from minus a to a. And we already kind of did this integral before. We know that the integral of the cosine function isn't going to contribute to this, so we'll just go ahead and cross it out and put in what we know what the answer is, because a squared, this is just going to end up giving you 2a. Solve for, let me not put it equals 1 there, but it is here and here. Solve that for capital A squared, and you get that a equals 1 over square root a. So that's interesting that a equals b. Pretty cool stuff there. And so we can write the wave function on this side. This is for the case where n is even. So root a, it's sine n pi x over 2a for even n. And we have psi equals 1 over, let me write this in black like I did the other side. We have psi equals 1 over root a cosine n pi x over 2a for odd n. Why am I terrible at writing? Odd n. Yep. And so that is a pretty awesome result. And it's cool because you can get the exact same thing as this. If you took what Griffiths got for the equation for the infinite square well with width of a, he got this wave function, and pi x over a. Obviously, it's different from ours because ours was from minus a to a, but he gives us a transformation to apply to his wave function that will result in our wave functions. Because you have, if you plug in x there, so you have that psi n is going to a sine n pi x plus a over 2a, which is a sine n pi x over 2a plus n pi over 2. Right. If you let n be even, so if n is even, then you're going to have sine of a thing plus an integer value of pi, which means it's still a sine function, except it's going to have a difference of sign. It'll throw a minus sign on there or a positive sign on there, depending on what you have. But you can just let that minus sign be absorbed into the constant, and you still end up with a sine function of n pi x over 2a for your wave function. But if n is odd, now you have a sine function that has our argument plus a half pi integer, which means it turns into a cosine function of our argument multiplied by some -1 to whatever, but you can just let that get absorbed into the constant a. And then you can normalize these again, but it's the same results if you do it at this point. So looks like we get the same results once we apply the transformation to Griffiths' equation, which is pretty cool. Now we need to sketch the wave functions. So I'm going to switch to a Desmos window. So here's a Desmos plot of the first 3 wave functions. So in red we have the wave function for n equal to 1. So this is going to be psi 1 here. You can see that it is just one hump of a cosine function. If you compare it to the figures that Griffiths made of his wave function for the infinite square well, it's the same sort of shape, it's just now spanning -a to a instead of 0 to a, but same shape and everything. Then psi 2, I set n equal to 2, you get this, again you get the same shape, it just spans from -a to a instead of 0 to a for that. And so then psi 3 I have here in purple, same shape, spans from -a to a. So the total width of the well is now 2a, so all of these figures have changed to reflect that, but the shape is the same for